Hello everyone, welcome to the part 2 of Unit 1 on crystallography. I am Sejal Lotlikar. Let's start. So in part 2, the things that are covered are simple crystal structures, reciprocal space and X-ray diffraction. Simple crystal structures. So we have included the simple crystal structures as sodium chloride, cesium chloride and a diamond structure. Now let's see the sodium chloride structure. NaCl structure consists of sodium and chlorine ions. It is FCC lattice with 2 atom bases. The reason it's FCC is that we can see here all the if we just forget about this red ions and if we just look at the blue ions, then we can see that all the ions are placed at the corner of a unit cell. Also, there are some ions at the face center. So, it is FCC lattice with 2 atom bases. Now, let's see the cesium chloride structure. So, in cesium chloride structure, we can see that it is like a simple cubic structure, and there is also another atoms like of the chlorine atom placed at the center of the unit cell. So this forms another simple cubic structure. So it is like a 2 interplanetary simple cubic structures of having the cesium ions at 0, 0, 0 and 1 chlorine ion at half of half. Now let's see the diamond structure. In diamond structure, it is also FCC lattice with 2 atom bases, and this is like all the ions are placed at the corner of a unit cell. Also, there are ions placed at the face center, so that forms one FCC structure. Also, there are at 1/4, 1/4, 1/4 coordinates, there are other ions placed, so that forms another FCC structure. So, diamond structure is the hardest structure in the world. It is one of the best known structure for its interplanetary FCC lattice. Now let's see what is a reciprocal space. A reciprocal space is a lattice in the Fourier space associated with the crystal. Every lattice structure has two lattices. Every crystal structure has two lattices associated with it. One the crystal lattice and another is the reciprocal lattice. Vectors in the direct lattice has the dimensions of length inverse length, and the vectors in the reciprocal lattice has the dimensions of length inverse. According to the Fourier expansion, the lattice translational vector n of r can be written as n of r is equal to sum of g and n of g e to the power I g dot r, where g is the reciprocal lattice vectors. And we must find such a set of vectors that are invariant under all crystal translations that leave the crystal invariant. So reciprocal space is nothing but its inverse space. So for example, if I have time space as t, then I can have a frequency space that is mu is equal to 1 over t. So these are two different spaces like frequency space and time space, and we can go from one space to another using Fourier transform. So the points in the reciprocal lattice are mapped by the set of vectors, that is g vector. So g vector is given by v1 b1 plus v2 b2 plus v3 b3, where v1, v2, v3 are integers. These integers are nothing but called as the Miller indices, and we are going to see what are Miller indices in the coming slides. A vector G of this form is a reciprocal lattice vector, and the relation between the real space and the reciprocal space is that B1, we can go from real space to reciprocal space using this relation, that is B1 equal to 2 pi A2 cross A3 divided by A1 dot A2 cross A3. So this A1 dot A2 cross A3 is the volume of the unit cell, and this A1, A2, A3 are the if A1, A2, A3 are the primitive vectors of the crystal lattice, then B1, B2, B3 are the primitive vectors of the reciprocal space. and we can use this property Bij is equal to 2 pi Kronecker delta Ij, where Kronecker delta represents when I is equal to j. When I equal to j, this Kronecker delta Ij is equal to 1, and if I is not equal to j, then this Kronecker delta Ij is equal to 0, right? So now let's see what is the Miller indices. As I mentioned in the previous slide, this V1, V2, V3 are nothing but the Miller indices. So how do we find this Miller indices? There's a certain procedure that we follow to obtain these Miller indices. That is, first to find out the intercepts of the plane, second to find the reciprocal of the intercepts, third we find the LCM of the intercepts. Now let's see how to find the Miller indices in the following examples. So considering this plane, I will take the the distance from the origin to the x-axis here as 1 unit, distance from origin to the y-axis as 1 unit, and since there's no intercept along z-axis, there's the intercept is at along infinity, so I will consider this intercept as infinity. So I can write the intercepts as 1, 1, infinity, right? Now I will take the reciprocal of the intercepts, that is 1 by 1, 1 by 1 and 1 by infinity. Then to find the LCM, so you can do like this 1, 1 and 0. So this 1, 1, 0 is the intercepts of the Miller indices of the these are the Miller indices of the plane, and similarly you can try here as well. So there is one intercept here along x-axis, one intercept here along y-axis, and there is one intercept here along z-axis. So the intercepts are 1, 1, 1. So now we take the reciprocal, so 1, 1, 1, and since there is no LCM along this one, so the Miller indices of this plane is called as is 1, 1, 1. So this is like the G vector, the reciprocal lattice vector has the intercepts 1 b1 plus 1 b2 plus 1 b3, right? Now let's go to another concept. This concept is called as Brillouin zone. So Brillouin zone is nothing but the Wigner seeds of in the real space. So as we saw in the previous video in our part 1, that in a real space the lattice has something which has for a primitive lattice we construct something called as Wigner seeds. Similarly, there is a similar construction which is associated in the reciprocal lattice that we call it as a Brillouin zone. So Brillouin zone is the smallest volume occupied entirely enclosed by planes that are perpendicular bisectors of the reciprocal lattice vectors drawn from the origin. Here is the Brillouin zone of the square lattice, and here is the Brillouin zone of the triangular lattice. The construction is similar to that of the Wigner seeds cell. So what we do is we join all the nearest neighbors, then we draw the lattice vectors, and then we find the perpendicular bisectors. And whichever is the smallest area enclosed, that is our Brillouin zone. So reciprocal space of 3D structures. So in 3D structures we have simple cubic, body centered cubic and face center cubic. Now let's see what is the structure in the reciprocal space. In real space, if a structure is a simple cubic, how it will appear in the reciprocal space. So as we know from previous video that primitive lattice vectors of a simple cubic structure are A1, A2 and A3 given by A1 x cap, A2 equal to A2 equal to A y cap and A3 equal to A z cap. So if we operate this using that formula which we saw in the previous slides, this B1 equal to 2 pi A2 cross A3 divided by A1 dot A2 cross A3. If we use all these things and if we try to find out what are B1, B2, B3 for a simple cubic structure, we find that the B1, B2, B3 also satisfies a simple cubic lattice. So, therefore, we can say that in a reciprocal lattice, the simple cubic structure remains invariant. So, it is the same. Reciprocal lattice for a BCC lattice. So, for a BCC, as we all know, the primitive lattice translational vectors of a BCC lattice are these, and the volume of a primitive cell can be found out using A1 dot A2 cross A3, and then using those relationships which we saw in the previous section, that these B1, B2, B3, using these formulas we can find out the primitive translations of the reciprocal lattices, and that to our surprise is nothing but the vectors associated with the FCC lattice. So we see that the vectors in the BCC in a real space, if some structure is BCC, then it's in the reciprocal space the vectors are of the FCC. Therefore, the FCC lattice is the reciprocal lattice of the BCC lattice. The first Brillouin zone of the body-centered cubic lattice is this structure, and the figure is known as regular rhombic dodecahedron. Now let's see the reciprocal lattice for a FCC lattice. And if we do the similar analysis for FCC lattice as well, like what we did in the previous section, like B1, B2, B3, if we try to find out the B1, B2, B3 for a FCC lattice, we find to our surprise that from if any structure is in the real space FCC, then in the reciprocal space it becomes BCC. Like the vectors which are found are of the BCC structure. You can try that and you can let me know in the comment section like how you can get a B1, B2, B3 in the FCC structure. And this is the first Brillouin zone of the FCC lattice. Now let's see what is X-ray diffraction. So according to the Bragg's law, it is 2D sin theta is equal to n lambda. So when a wavelength of radiation comparable or smaller than the lattice constant, we may find the diffracted beams in direction quite different from that of the incident direction. So we see here all the incident radiations are falling on the crystal planes, and some of them are reflected back. So the path difference, that is 2D sin theta, is equal to the n lambda. So that is the when lambda is the wavelength of the X-rays. So we do get a pattern which we find out like there are many dots which are formed, and using a detector we can find out the intensity of the bright and dark spots. So X-ray diffraction is used to know the structure, phases, preferred crystal orientations, and other various structure parameters such as average grain size, crystallinity, strain, and crystal defense. Also, it serves as a fingerprint, like it is very unique. Every crystal structure is unique. So if we have synthesized anything, if we want to know whether that synthesized thing is proper in structure or not, we find X-ray diffraction of that sample, and then we match that to our the database which is available for that structure. So here is a typical image of the X-ray diffractometer. Here is the X-ray source. So we have a sample here, and the X-rays are passed on the sample, and after diffraction all the rays get we can detect the rays using a detector, and the detector can move in the 2 omega direction, and we find out the intensity versus the 2 theta graph for a X-ray diffraction pattern. And here is a Rigaku X-ray diffractometer. So here we can see that here is a target sample, and like here is the source from which X-rays are generated, and these X-rays fall on the sample here. Here is the goniometer, this samples where sample is placed, and they are getting reflected, and then they are detected by a detector. Here is a typical diffraction pattern of KCl structure. So KCl has this kind of pattern of X-ray diffraction. Thank you so much and have a good day.